Thank you for staying here until Friday afternoon. Probably I will reduce a little bit my talk since you are still late. My choice is to focus on the stuff that were promised yesterday. Okay, when I told you yesterday or this morning by Philippe, I will show you this today. So I will try to focus on this and maybe skip some other stuff that I plan to show you. This will take maybe 10 or 15 minutes. Okay, so there will be two parts today. The first part is the follow-up of yesterday, but on cardiac valves, to show you how some ideas that were presented yesterday can be used for the difficult problem of cardiac valves. And in the second part, I will address some data assimilation problem in infrastructure. So, as I said yesterday, cardiac valves raise several difficulties: large displacement, fast dynamics, high pressure drop, isovolumic phases when all the valves are closed, and change of topology because of the contact. Okay. Today I will show you quickly a first very simplified approach for cardiac valves, which allow us to run simulations in reasonable time for practical applications. Okay, and in the second step, I will show you a brand new coupling algorithm for cardiac valves based on a formulation with Lagrange multipliers. So our first approach, which is, as I said, very simple, straightforward, efficient, but not with fluid structure interaction, is the following. We will consider the Navier-Stokes equations, and we will cut the domain in two parts where are the valves. Okay, and where are the valves? We put some sort of resistive terms. Okay, so the idea is simple. It introduces a discontinuity of the pressure through the valves. Okay, and we will play on the coefficient here to decide if the valve is open or closed. So typically, we have two positions, one in the closed position, one in the open position. Okay, and with some simple criteria on the hydrodynamics, pressure drop negative or backflow, we decide whether this resistive term we add on these two sets of surfaces is 0 or say large. Okay, so that's a very simple approach, and there are some say algorithmic stuffs, but I will not detail it too much. Of course, the drawback is that there is no valve dynamics, and the position of the valves have to be chosen. But in most medical images, you can see the valve only when they are closed or when they are open. Okay, you cannot follow the dynamics. So we can also say that the level of complexity of the model is adapted to the level of precision of the data we typically have. Okay, and of course there are many advantages. With respect to full FSI, it's way more robust, efficient. We can handle a very accurate transvalvular pressure drop, which is an important aspect. And compared to other approaches in the literature where people just use the 0D model, here we have a reasonable jet outside the valves, and there is no boundary condition artifact, in the sense that when the valves are open, since the valves are immersed in the 3D fluid, when the valves are open, you do not have an artificial boundary condition. Whereas in the literature, most often people play only with boundary condition, which of course affects the flow where you are interested in. Okay, so here is the formulation. And the idea, since we decided where to put the valves, is that we can double the degrees of freedom on the surface of the valves, which allow us to capture the pressure drop, which is very important. Okay, so here is an example, in a toy example, okay, where you see that the pressure is really discontinuous when the valves are closed. This is the pressure elevation. Okay? And to show you that we can actually play with the geometry to get different jet shape, in that case, we simulated a stenotic configuration, which means that a valve does not open fully, and this affects the jet, and this has some consequences on some pathology of the aorta, and you can see that the jet here is actually modified. Okay, so that's a very practical approach, but it allows us, for example, to do this kind of simulation in the heart. So these are the simulations presented by Philippe this morning. Okay, that we can use as boundary condition on the fluid domain to get this kind of hemodynamic simulation. So on the left, it's a normal condition. So you have the flow entering from the atrium here in the ventricle and then ejected through the aortic valves to the aorta. Here, this is a pathological condition that I mentioned yesterday. This is the pathology we are interested in our collaboration with Philips. You can see here that the mitral valve is regurgitating. Okay, there is a regurgitation that can be easily modeled with this kind of simple model. Okay, so when we need, efficiency, robustness for application like the one with Philips, this kind of simplified model are very interesting. But of course, we are also interested in the challenge of doing the full real fluid structure interaction on the valve. And for that, we will adopt a situation where the two meshes are independent. So this is a non-body fitted approach, contrary to ALE, contrary to what I presented yesterday. Okay, here we will have two different meshes, one for the valves, one for the fluid. This allows us to handle very large displacement without remeshing, and this also allows us to handle the change of topology when there is contact. There are many difficulties. First, it's difficult to avoid the leaks through the valves to capture the correct pressure drop, because now the meshes are not compatible. Okay, so we cannot easily double the pressure, except if you do some sophisticated stuff like XFEM, okay, but that's not the case here. And until recently, efficient partition coupling were not available, and that's what I will present you today, based on some result I presented you yesterday. There are two ingredients. The first one is the choice of the Lagrange multiplier that will be used to enforce the continuity of the velocity. So the continuity of the velocity at the fluid structure interface is enforced in a weak sense here, and we have to choose the space of Lagrange multiplier. Okay. Of course, in that case, the Lagrange multiplier is, if you have a valve, is the jump of the pressure of the stress, okay, through the valves. The typical choice in this framework that was proposed in particular by Glowinski and co-workers is to use L2 Lagrange multipliers, which is a reasonable choice where you can prove some in-stup stability result. Okay. Our choice is a bit different and a bit strange in a, say, variational finite element framework, is to use Dirac measures for the Lagrange multiplier. This is not very common. Of course, it requires more regularity, but this is typically satisfied as soon as you use a continuous finite element, which is our case. Okay, and the theory of that has been done, not for the fluid equation, but in some simpler equation by Bertrand Maury and then Benoît Fabrège. And so there is a theory behind this choice, okay, of Dirac meshes as Lagrange multiplier. That's our choice, and you will see that it's very simple actually, okay? It just means that choosing Lagrange multiplier on the point of the solid means that you will enforce the velocity of the fluid on the point occupied by the solid, okay? It's just that. You can call it collocation, it's collocation. Collocation in a variational formulation. So in practice, this is very straightforward. All you need is to be able to compute the local coordinates of the structure point in your fluid element, which is usually not a trivial, but something that can be done, okay? So you just have to compute this interpolation matrix K, and that's it. So if I just simplify the notation, denoting the velocity unknown just by U, okay, I drop the pressure for simplicity. So at the end, you get this kind of saddle point problem to solve. Okay, K is the interpolation matrix, lambda is the Lagrange multiplier, and U denotes the fluid unknowns. So this is the saddle point problem, so with the traditional difficulties of saddle point problem. And there is another difficulty here, that the pattern of the matrix is changing, because when the valve moves, okay, the pattern change, of course. So it's a practical difficulty. Just since yesterday, I spent some time about the computation of the load in the case of non-compatible meshes. In that situation, we introduced, you remember, these K interpolation matrix, just to insist on the differences. Here is the formulation I presented you yesterday. So RF is what I called yesterday the variational residual, you remember? And here is the formulation today, okay? So there is some sort of formal similarity, but it's only formal, okay? Because yesterday the problem was not solved as a saddle point problem, okay? So the first approach to solve the saddle point problem is to do a regularization by penalization. So you replace the 0 here by an epsilon, and this is very standard. And you get this, so you eliminate the Lagrange multiplier with your penalization, and you get this system to solve. There is a nice property which is very surprising at first with this system, is that the new matrix here is actually included in the sparse structure of the classical matrix, which is not that obvious, okay, because you have an interpolation matrix of something that is moving, okay, you multiply it by transposed. At the end, you can be afraid to have something that is complicated to compute, and you have to add some new entries in your matrix, which complicate not only the implementation, but also which can reduce the efficacy of your preconditioner, so that's a serious problem. Here there is a sort of miracle which makes that this matrix has its sparse pattern included in the sparse pattern of the standard matrix, and this is really a direct consequence of the choice of the Lagrange multiplier. Okay, if you take Dirac meshes, you have this property. If you take piecewise constant function, for example, L2 function, you do not have this property. So that's a very interesting aspect of the method. But of course, as usually in penalization methods, you have a Hill conditioning, which for us is absolutely critical, especially when you have change of topology. Okay, and still we need an efficient coupling scheme. Until recently, we had nothing better than the very basic fixed point iterations that I presented you yesterday, that were used 15 years ago and cost 30 times the cost of a fluid and solid solution. Because all the other solutions that I presented you yesterday are very difficult or even impossible to adapt to this formulation with these Lagrange multipliers. Okay, so really until recently, we were stuck to very old coupling scheme for this kind of problem. So I keep the same framework as yesterday, distributed computation, where we only exchange some quantity, in that case, velocity and Lagrange multiplier. I will not address today, because of lack of time, the question of contact, but just want to mention that the contact can be handled with our algorithm with the same kind of distributed approach, in the sense that when we exchange the hemodynamic force here, there is a sort of contact master that will decide if there is contact or not between the solid, and which will add to the hydrodynamic force the contact force. Okay, and so the solid receives the forces without even knowing that there is a contact force. Okay, so from the point of view of the solids, there are several valves here, okay, valvules, okay. So from their point of view, they do not know if what they receive is a force due to the fluid or force due to the contact. This is handled outside, which is very, very convenient. From a practical point of view, you have to imagine here that probably during your test, you will want to change between several structural models and so on, maybe different codes. You do not have to worry about contact. This is handled outside. Okay, so let me show you just some simulation that were done with this approach with penalization, so which means a huge computational cost and difficulty to handle the contact pressure because of this conditioning problem. That's a serious problem. Conditioning is really a serious problem when the valves are closed. Okay, so these were our where we were a few years ago, and now we have really done a big step with this new FSI scheme, which is fully explicit, and I will present you the main idea. So this is the problem we want to solve. Just like yesterday, we have a solid here, we have a fluid here with this Lagrange multiplier formulation. So you have to remember that we use here Dirac-Messi's Lagrange multiplier, okay? And K is the interpolation matrix of the structure nodes in the fluid domain. And we want to split these two equations in order to solve them iteratively, only once per time step. Just a reminder about the last scheme I presented you yesterday, the scheme by Miguel Fernandez called the Robin-Neumann scheme, adapted to thin structures, which is exactly our case here, okay? So the idea was to combine the equation of the solid and the continuity of the velocity in order to reformulate them as a Robin boundary condition for the fluid. Okay, this was the idea I presented yesterday. So we will reformulate this idea in the formulation with the Lagrange multiplier. And to do so, just for the sake of explanation of the methods, I will introduce an intermediate, so sort of provisional velocity that will be not used at the end, okay, just to understand. So this is our fluid problem, and what would be the Robin boundary condition for the fluid problem? If I go back, the Robin boundary condition means a combination of U, the velocity, and the stress, expressed as the structure, variable, and operator, okay? So if I try to mimic this Robin boundary condition in this Lagrange multiplier formalism, this is quite natural to write this like that, okay? Because here you have U, the term coming from the inertia of the solid. This is the stress, so the equivalent of the sigma n of the previous equation. And these are the terms coming from the solid equation. Okay, so this is really the mirror of the Robin boundary condition in this formalism. But then we can do some sort of manipulation of the equation. First, we can eliminate this provisional step velocity here. Okay, so you just plug this term here. And with this will allow you to eliminate the Lagrange multiplier. Like yesterday, you remember I told you that this is not very convenient in the fluid to have the structure operator, but the structure operator can be eliminated with the structure equation. This is what we do, and at the end of the computation, what you get is an expression of the Lagrange multiplier as a function of the fluid velocity at the current time step and of previous solid velocity at the previous time steps. You re-inject this in the equation, and you get this scheme, which has very nice property. And first property compared to penalization is that the coefficient here now is no longer 1 over epsilon. It's no longer something that will be very, very large. It's something that is related to the physics of the problem. Okay, that's the first nice property. And the second nice property, again, is as soon as you decide to do mass lumping, okay, mass lumping is just replace the mass matrix by something which is diagonal. Then you recover the property of the Lagrange multiplier Dirac-Messi's, okay, to have this K transpose K matrix to be in the sparse pattern of the original matrix. These two properties are extremely convenient, both for efficiency and for convenience of the implementation. And then you can solve the solid. Okay, so you just solve the fluid once and the solid once. And it works, and we even have a theorem to show that shows that the scheme is stable, actually, in the energy norm. Okay, so that's really a big step in this field because we reduce dramatically the computational cost, but not only. It's not only a reduction of the computational cost, it's also an increase of the robustness, especially at the moment of contact. So this is an example of where we compared with implicit with explicit, just to show that we get the same result. But more interesting is this example, where we compared two methods, one which is known to be extremely accurate, which is niche XFEM methods, where you compute explicitly the pressure drop, but at the price of difficulty of implementation. So the test here is done in 2D, and in the group we are not yet able to do it in 3D. Okay, with this implementation, which is quite simple, we are able to get the same kind of pressure drop and a very similar result for the displacement, including when there is contact. Okay, so here this is the Y component. Okay, so these plateaus correspond to contact, and you can see that we obtain a very good accuracy with the explicit scheme here. Okay, just to finish with this valve stuff, let me show you some first simulation in 3D, but this is really ongoing work, and we are not yet able to run it with physiological values. And just to insist on the fact that we are still some stuff to fix, is that there is a really difficult problem of mass conservation. At the moment, what we use is we use a trick which consists in boosting the gradiv stabilization near the valves, which is a trick proposed in this paper. But again, this raises conditioning issue. So there is an ongoing work. We have an idea to fix that, but we still have to work. Okay, so I will stop here with the valves and with the forward problem. I can take questions if you have at this stage. No? Everything is clear? Yeah?
I think maybe I missed is why do you have a Lagrange multiplier in this problem with respect to what you showed yesterday?
Yes, because yesterday we have something which is topologically simple in the sense that it was a wall, okay, around the tube. Okay, so in that case, even except if you have very specific problem, maybe in aeroelasticity, it can make sense to have non-compatible meshes because you have very thin boundary layers in the fluid compared to a solid where you can use much larger elements. Honestly, in that cases, it's straightforward to use compatible meshes. So as soon as you have compatible meshes, the transmission between the two problems are not complex. You do not need to have this machinery of Lagrange multipliers and so on. Whereas here, since we have incompatible meshes, we have to decide what to do. Yeah. Okay?
I have a question.
Yeah?
I wanted to ask if you develop your own algorithms to solve this kind of problems, or are you using software that solves the FSC problem?
No, this is our own algorithm. Oh, yes, I think I understand. Your question is whether if we use some... Exactly, I see. So that's an important question. Actually, in many labs, people are using some sort of black boxes code to solve fluid and solid, okay? And this raises interesting question from the point of view of coupling, because when you use black boxes, you have a very minimal interaction with the code, and therefore some of the algorithm I've presented you cannot be used in that case. And basically what people do in that case is often to go back to the fixed point methods used 15 years ago. So that's a crucial question, because that if your constraint is that you cannot change the code, it restricts the possible scenarios. Yeah.
And you are developing your own code under Hennenfent or Statistical, which kind of?
No, it's a research code developed in the group. Okay, some of the algorithms were also tested in FreeFrame. So if you are interested in a FreeFrame script of this algorithm, we can share them.
Okay. Yeah. Because I developed also under FreeFrame.
Okay. Yes. Yeah, that's something we can share. Okay. No more questions? Not too difficult with the French fries and the dessert at lunch? Okay. Okay, so let's go back to the inverse problem. And many stuff were introduced by Philippe, which is nice, because then I can go straight forward to the applications. Let me show you these two movies. On the left-hand side, it's a simulation that is done on the anatomy that is on the right-hand side, which comes from a CT scan. And you can see that different kind of information can be found in the two simulation, okay, or in the two movies. On the right-hand side, you have access to some sort of noisy reality about and the displacement. On the left-hand side, you have access to also the displacement, but also the forces, the pressure, and so on. Okay, so the idea of medical data assimilation will be to try to mix the two approaches, and of course you can mix them. Here I only show you the displacement, but you can mix them with other kind of modalities, like for example velocity field that can be acquired with a PC MRI. Here the valve movement that I've shown you yesterday, ultrasound, or even sometimes catheter, which gives you the pressure. Okay, so the idea is that on the one hand you have a model, Navier-Stokes equation, solid mechanics, and so on. On the other hand, you have measurements, CT scan, MRI, ultrasound, phase contrast MRI, catheter, pressure, and so on. Okay, and what you want to do by mixing these two kind of information is first to reduce the uncertainty you have on the parameters of your model, for example, the arterial wall stiffness, boundary condition. So estimate the parameters. If you are confident in your model, you will rely on it to access to some quantities that are hidden from the point of view of the measurements. Okay? If you are able, for example, to measure the velocity, and if you are able to mix it with the Navier-Stokes equation, then the Navier-Stokes equation will give you access to the pressure. The pressure in that case is a hidden quantity. Or if you can measure the pressure at one place, maybe your model will give you access to pressure at another place. Or the stress, that's typically a hidden quantity in images. And the third motivation can be also to improve the measurement by regularization or interpolation. Okay, it can be seen as an expensive way to denoise the problem. And when I talk about noise, it's not only the noise on the images, but for example, when you have a velocity field that are supposed to be measured by an image, you can just ask yourself if the divergence of this velocity field is zero. Okay, it's supposed to be zero. The fluid is for sure incompressible, and in practice it is not. Okay, if you take directly the measurements, you do not have a divergence-free velocity. So if you do a mix with a model which enforces from the measurement the divergence-free velocity, then you improve the measurement you have, or you denoise if you want the measurement you have. Okay, so I will start with some very basic reminders. Most have been already presented by Philippe, just to have the notation. Okay, so you remember in the Philippe Moirot presentation, we have a general dynamical system. In our case, the state variable x will be the fluid velocity, the solid displacement, and the solid velocity. Okay, so you can see a huge state variable. And the parameters, theta, are typically the fluid density, fluid viscosity, the Young modulus, so the stiffness of the arteries, for example. And of course, we have an imperfect knowledge both on the initial state, x0, and the parameters. We have an imperfect knowledge, which means that we have an a priori knowledge, but also an unknown part, and the purpose will be to estimate this unknown part, both for the state, the initial state, and the parameters. To do so, we have access to measurements. So we have this H operator. With a DAG, I will denote the true solution. Okay, you can imagine the DAG as a T. Okay, so the T like true, the solution that we do not have access to. So the operator H is applied to the true solution, and it gives you up to a noise the observation. For example, you can imagine that you measure here the flow rate through a surface. Okay, so the operator H will be typically the integral on the surface of the velocity field times the normal. And this is the measurement you have. And the purpose of data assimilation is to minimize two quantities, the sum of two quantities. First, the data misfit, which means that I want to find the state variable that are such that the observation applied to my state variable compared to the true observation are as small as possible, okay, are as close as possible, so the discrepancy is as small as possible. And also, these quantity have to be a priori small if you have a good prior. If you have a good prior, you expect that the perturbation of your prior will not be huge. Okay. And one very important aspect is that here there are some norms. So you can put very simple norm if you want. You can put a L2 norm, for example, but in front of them you can put a coefficient. And the coefficients in front of these two kind of terms will measure the confidence you have either on your prior or in your observations. Another reminder is that formally the difference between state and parameters can be forgotten, in the sense that you can consider that your parameters are some special states variable with zero dynamics, okay, which this allows you to reformulate the problem in state and parameters just as a problem of state estimation. This is purely formal, but this is convenient for the presentation. And so what you want to do is to minimize these formula. And just to insist on something that Philippe said yesterday, is that even if you think you have a linear problem, your problem is most often non-linear. Okay, just think of this very trivial equation. For anyone, this equation is linear. Okay, so do not think that you can use a linear like a Kalman filter for that, because what you want to do, since you reformulate your problem and you want to estimate the state and the parameters, what you are interested in practice is not this equation, but this one, where you have considered the parameters as new state variables without dynamics, and therefore you can see here that your system is not linear, and therefore you really need some extension of a linear algorithm. Okay, and as Philippe said, we have two family of methods, variational approaches, which consist in minimizing these cost function by introducing gradients, which are often based on adjoint equations. Okay, so in that case, you need typically several direct and backward resolution of the problem and its adjoint, or sequential methods or filtering methods, where you introduce this term. Okay, so you consider a modified equation. You can be surprised saying, okay, my equation is the black one. I do not want to solve the black and blue one. Okay, your physics is in the black equation, but think that if everything goes well, at the end, your solution will be such that it will match the observation, and therefore this term will hopefully vanish. Okay, this is the purpose. The purpose of data assimilation is to make this term vanish. Okay, and so the difference is, okay, in the case of variational methods, you solve several successive full problems. In the case of sequential methods, you adapt your parameters and state along the time, okay, and so you converge hopefully to the same quantity in some cases, okay, but in general it's not that way. The question is how to construct this operator J in sequential methods. So Philippe has shown you the Kalman approach and the Leuenberger observer. So I will come back to that in the specific case of fluid structure interaction. I should say, before doing that, good question is it reasonable to try to do that? Okay, in other, is your system identifiable? Okay, and that should be that must be the first question you ask. Are my measurements sufficient to estimate the parameter or the state I want to estimate? Okay, so I will not address this question here. I give you some references. The first one is very general, gives you an overview of a different way to define identifiability and how to test it, because there are different kinds of identifiability. The second one introduces a practical way to test identifiability, which is convenient in practice, at least for some for small dynamical system. Okay, and the third reference showed an application of this approach to hemodynamics problem. So if you are interested in identifiability in hemodynamics problem, you can have a look at these references, but I will not address it today. Okay, so I will use extension of the Kalman filter since our problem is nonlinear. And as presented by Philippe, I will use unscented Kalman filter. So I will just focus on the very practical aspect. With unscented Kalman filter, we talk about particles. What mean particles in that case? That very simple is just an instance of your solver. Okay, assume that you have a parameter which is, for example, the Young modulus that you want to estimate. You will run your code with different value of Young modulus. Each run corresponds to what is called a particle in that framework. Okay, so modify a bit the Young modulus, do a time step. Modify a bit the Young modulus, do a time step, then you have two particles. Okay, so you can run several instances of your code in parallel very easily with these different values perturbated. Okay, so when I say propagate NP particles, just mean run one step of your code with different value of the parameters you are interested in. And then you do some empirical means. Okay, you take the average of the different solution you get after this step. You can do the same for the covariances. Okay, and then by analogy with the Kalman gain, okay, you can define a gain by this quantity. So the formula obtained very in a straightforward way by doing empirical averaging, and then you can combine them to get the equivalent of the Kalman matrix. So you see the advantages. There is no tangent operator. Okay, you do not have to compute the derivative of your problem. Think of fluid structure. It means a lot not to have this to compute. And it's very easy to parallelize. Okay? If you have to run 25 particles, you just launch your code on 25 processors and just get the solution at the end of the time step, do the average, and that's it. Okay, okay, maybe I will skip that to save a bit time. It's just the idea of how to perturbate the state variable or the parameters on each particles with the UKF, but I give the reference. Okay. So you remember that our goal is to use it for fluid structure interaction. So with a huge state space and potentially with several parameters. Okay, and we will take measurement like typically the one that are available on medical data. The major concern of this approach is that the K matrix is full and huge. Okay, so it cannot be used directly for the PDEs. And so, as Philippe explained, we will mix this approach with the Leuenberger. Okay, so the Leuenberger approach will be used for the state. The UKF approach will be used only for the parameters. So the Kalman approach is restricted to typically 10 or 15 values. Okay, and whereas the state variable are handled with a feedback term put on the equations, which fits in very well in the finite element formulation of the equations. Okay, so this is the basic idea. I give you the reference where these stuff were introduced in mechanics. In other fields, this was also used in different ways. Okay. So again, the implementation rely on the same spirit that I presented you for the fluid structure. We keep the code separate. Okay, so this is here you choose your favorite fluid structure algorithm. Here you add some observation on the solid. For the moment, we have only observation on the solid. Okay, and then you can send the states and the parameters to an external solver that will take care of the data assimilation algorithm. And again, this data assimilation algorithm needs to run several instances of the solvers. So it means that actually in practice you will have several simultaneous execution of your codes. Okay, and typically if you have 10 parameters to estimate with the UKF, you will need 11 simultaneous execution. Okay, so if you have 11 processors, okay, it's the overhead compared to the direct problem is very limited. Philippe told you that when a direct computation takes 1 day, an inverse problem takes only 1.5 days. Okay, so that's very efficient. Of course, it's a bit cheating because I compare something which is parallelized for the data assimilation with something which is not parallelized for the direct problem. Okay, but try to parallelize methods which include an adjoint and so on, and then we can compare. But the work is really different. Okay. So now I will focus, so this was a few reminders of what Philippe already presented. Now I will focus on the Leuenberger estimate for specific fluid structure interaction problems. And the Leuenberger filters are very, very nice. They look simple, okay, it's just a feedback force, but there is really room for creativity, and there is some pitfalls also. Okay, so I will emphasize both aspects on the specific problem of fluid structure interaction. So first, I remind you the basic idea on this simple linear problem. So this is the real dynamics, okay, and the question is how to devise J, is my J efficient, okay? So since that's the real dynamics and that's the real observation, so this is 0. And this is my observer, okay? So here this is not 0 in practice. Since everything is linear, you can do the differences between the two equations. So the error between the true solution and the one you are computing satisfy trivially this equation. So you can do a linear stability analysis of this equation. So you compute the eigenmodes of this operator, and you will analyze the real part of the eigenvalues. And the purpose is to have a G operator such that the maximum of the real values of the real parts of the eigenvalues is as small as possible, in order to have something which goes quickly to 0, in order to have a quickly vanishing error. Here you can say, okay, when we have dissipative system, we forget the error on the initial state. Okay, so is it really useful to accelerate this process? The answer is yes, because think that you are estimating simultaneously the state and the variable, and you want to reduce the state as fast as possible in order not to perturb too much the estimation of the parameters, the state and the parameters. Okay, so typically, if you want to reduce the initial error by a factor beta, for example 10, after 0.1 second, then what your target will be to have a maximum value of the real part of the eigenvalue, which is -25, okay, just to have an idea. So let me remind you the work by Philippe Moirot, Dominique Chapelle, and Patrick Le Tallec about what you can do when you have a measurement on the velocity. Okay, assume that you have a measurement on the velocity. Then the idea is quite simple. You can put a force on the right-hand side, which corresponds to a sort of feedback. Okay, it will force your system to match the measure of the velocity. And this is what they call the direct velocity feedback. You can compute, again, the system is linear, you can compute the error. Of course, the error will be reduced by this term. It can be shown just on the energy equation, but be careful. We cannot be naive here, okay? Choosing this gamma parameter is critical, and do not think that the larger is gamma, the better it is. First, think that you can have noise here, and so if you have noise and you multiply it by a huge value, it's not good, okay? But you can also think of this trivial example, so sorry for giving such a trivial example, but okay, this is a linear oscillator. Okay, so the equivalent of the feedback term will be this damping term, and it is well known that if you increase the damping on such a linear oscillator, then you will have, of course, a reduction, a damping of your signal. So if you look at the eigenvalues, the real part of the eigenvalues will be reduced when you increase the coefficient gamma, which is good. This is what you want. Okay, so you keep increasing gamma. But then you reach the critically damped system, okay? And then if you keep increasing gamma, what happens? Okay, you have an eigenvalue which goes back on the wrong direction. Okay, so we cannot be naive. Even in absence of noise, choosing the correct gamma is not something trivial because there is really a critical value that you are looking at. Okay, in that case, this is simple. In general, it's more complicated. Okay, so this is what they propose when they have measurement of velocity. Now assume that you have measurement of pressure, of displacement, which is much more usual. Then first idea could be to do the same. Put a sort of feedback force on the equation here, on the equation of the momentum, okay? And actually, this is what is done, especially in the medical imaging community. People call that image force method. And actually, it does not work very well. And it's even quite a poor behavior that you get usually when you do that. And as I said, there is room for creativity, and what they proposed was very strange at first. Okay, so it was, they called it the short displacement feedback. Instead of putting this feedback term in the first equation, they modified the relationship between the displacement and the velocity. So in that approach, the velocity is no longer the time derivative of the displacement, which look weird. Okay, but remember, if you are able to do what you want, in the sense that you are able to assimilate the data and correct your system, at the end, this term will vanish. Okay, so, and you will recover the correct equation. There is another idea that I will not detail here, which consists in modifying the norm that is used to measure the discrepancy, okay, which is also tricky. And I will come back to that question for fluid structure problem. Okay, so the velocity is no longer the time derivative of the displacement, and the norm matters. This is what you have to take in mind. And so if you do that, you can obtain the same sort of result for the displacement measurement than for the velocity measurement because of this trick, okay? Because this was done in a clever way in elastodynamics. And now I want to see what happens in fluid structure. So again, I will limit myself to measurement on the solid only. Okay, I will assume that I do not have measurement on the fluid. And I'm interested in the effects of the fluid structure coupling. There are two other important questions, which are the effect of boundary condition and dissipation in the fluid. I will not address them given the time today, but I will emphasize what happens with the FSI coupling. So I consider a very trivial test case, which consists in inflating a tube and see how the tube goes back to rest, okay? So it's like if my observation is a tube at rest, and I want to go back as fast as possible to this observation, which is the fluid at rest. Okay, so I want to, okay. And the surprise is the following. The results we obtain with measurement on the displacement are way better than the results we obtain with measurement on the velocity, which is strange because when you do not have a fluid structure coupling, when you only have a fluid, it's usually the other way around. Okay? At most, you get the same kind of convergence, but usually when you have displacement measurement, it's more difficult to handle that velocity measurement. Okay? So we wanted to understand why, because of this fluid structure coupling, we have this discrepancy. So I said that I will skip the case in hemodynamics when we observe the same kind of problem. And so we did the analysis on our favorite toy model, which is exactly the same as the one I presented you yesterday on the added mass effect. So I assume that the fluid is just limited to this very simple equation. Again, I can write this equation as a Laplace equation of the pressure. Again, I introduce the Steklov-Poincaré operator, which is a Neumann to Dirichlet operator, to have an expression of the pressure as a function of the acceleration. Okay, so this is exactly the same framework as yesterday. And as yesterday, this can be used to replace the boundary condition on the solid with this Steklov-Poincaré operator, and therefore to write the fluid structure problem in a compact form when you have on the top of the mass, classical mass matrix of the structure, this non-local Steklov-Poincaré operator that multiplies the acceleration of the solid. Okay, so this will be our toy problem. And on this toy problem, what we will do is to test the two approaches. What happens if I have velocity measurement? What happens if I have displacement measurements? And let's see what we get. Okay, and the analysis of the eigenvalues confirm the observation. You can see that when you have velocity measurement, you only improve a bit the eigenvalues in the sense that the real part becomes slightly more negative, but not that much. Okay, whereas when you have displacement measurement, then when you increase the value, the eigenvalues goes really negative. Okay, so this confirms the observation. So at least we have on this toy model what we observe on the nonlinear model. So this is a good starting point. And next, if you want to understand a bit more analytically what happens, you can have a look at the sensitivity of the eigenvalues with respect to the gain coefficient. And what you get in the fluid structure case is that you get this formula. Okay, so in the case of displacement measurement, the gain, the sensitivity is -1/2. Okay, whereas assuming you have full observation, this is a simple case. Okay, and in the case of velocity, what you get is this added mass operator here. And again, in the blood flow, we are in the bad situations. It's a bit like yesterday with these coupling schemes. This may work in some situation. In blood flow, we are in the bad situation where this quantity is close to 1, which means that the eigenvalue sensitivity is close to 0. And this is exactly what we observe here. They do not move a lot when you change gamma. Okay? So once we understood that, then give us an idea to change the norm to measure the misfit in the fluid structure case. And then you realize that if you modify the norm here, if instead of taking the L2 norm, you take something which takes into account this non-local operator, then you recover the sensitivity that you get with the displacement measurement. Okay, so again, this is an illustration of the fact that, okay, Leuenberger filters are simple. There is really room for creativity. Okay, you think, okay, what can I do best than taking the L2 norm of the difference or H1 norm maybe or whatever, and then you look a little bit around the problem, you see that you have troubles and so on, you try to understand them, and then you end up with an idea which is not, which is quite surprising, okay, that you have to modify the norm here, including this added mass effect directly in the way you measure the discrepancy. And this is confirmed by numerical simulation. Okay, if you take, so this is the standard way to do. So here the eigenvalues do not move a lot. This is the corrected way to do. Then you recover something which is quite efficient. Okay, and I said that I will illustrate the fact that we have to be careful. There are some pitfalls, and this is an illustration. You remember what I said? With the SDF, we have this strange property that the velocity is no longer the time derivative of the displacement. Okay? So when you are interested in fluid structure coupling, you are interested in the velocity, but which one? Okay? So when you say at the fluid structure interface, the fluid velocity matches the solid velocity. Yes, but which one? Is it the solid velocity or the time derivative of the displacement? Now they are no longer the same. Okay, and this is critical because you can do an analysis that shows you that really you have to take what is called velocity in the fluid, in the solid, and if you do not so, you kill the efficiency of your filter. So that's clearly a pitfall. Okay, you really have to be very careful on the variable you consider for the coupling with the fluid. Okay, so I said that I will skip the stuff related to specific to the boundary condition and the viscosity, and so I jump to the conclusion on this part. Is that so? When you have a velocity measurement, so we basically have three things to understand: what the difficulty due to the fluid structure coupling, the difficulty due to the fact that we have dissipated boundary condition, the difficulty due to the fact that we have dissipation in the fluid. Okay, so when we have velocity measurements, we had trouble for the two first parts, and we found a solution for the first problem. So the difficulty due to the fluid structure coupling and the added mass. So that's good. When you have displacement measurement, it's okay. As soon as you understood that you have to take the velocity of the solid for the coupling. If you take the time derivative of the displacement, it's wrong, okay? And then the real trouble is that when we use dissipation in the fluid, when we have a real fluid, say, then for the moment we do not have any satisfactory solution. So there are, of course, some ideas to address this, but at the moment this is not yet done. Okay, so there is room here again for new results. So first thing is that we checked that if we add a pressure measurement on the boundary condition and we add an observer on the boundary condition, then it fixed the problem, but it's not obvious to get pressure measurements in practice. And of course, if we can handle fluid measurements, then probably it will improve that. But again, this has to be done. Okay, and in the minutes I have, I will finish with some application to blood flow of all these machinery. So let me start with a synthetic example. So in that case, I will generate myself the data, and I will test the result of the data assimilation, knowing the results since I have generated myself the results, okay? So here we have 5 different zones on the wall with 5 different stiffness. I run a simulation which is quite realistic in the sense that it is done with all the physiological parameters, with these 5 different stiffness on the boundary. So this is a full FSI problem, even if it's difficult to see it. So you have an inflation of the aneurysm here. Okay. Since I use synthetic data, of course I will add some noise, and I will do resampling on the observation. And just to show you, the dashed line here represents the displacement that is added as a noise to the synthetic measurement. So it gives you an idea of the signal-to-noise ratio, and it shows you, for example, that in region 3, the red one, the signal-to-noise ratio is quite high. The noise is small compared to the signal, okay? Whereas, for example, in region 1, the blue one, you see that the displacement is quite small compared to the noise, so the signal-to-noise ratio is poor. And we will have to fix 2 parameters. The one which governs the confidence we have on the a priori knowledge on the parameters, and the other one, the confidence we have on the observations. Okay, so when we run the data assimilation with all the algorithm I presented, this is the kind of result we get. So here we know the solution. So the solutions are the dashed line. So this is the values of the stiffness of the Young modulus of the different zones. So we have 5 values to recover. As you can see, this is a sequential method, so the value will change with time. We start from a value which is reasonably far away from the one we are looking at. We are looking for, and you can see that after a while, the convergence is very good where you have a good signal-to-noise ratio. The convergence is less good when you have a bad signal-to-noise ratio in the region 1, okay, in the blue region. You are quite far away from that. And of course, the solution depends on the parameters. And this is something we have to deal with. If you take different confidence on your parameters or on your observation, you get different answers, which is a bit annoying, okay? But, okay. Hopefully, we have some criteria to be informed about that. Here, I focused on the best region and the worst one. Okay, so if I take these parameters, this set of parameters, you can see that the convergence is not bad. It's quite accurate. And the light blue lines here indicate the value of the covariance of the estimation. Now, if I change the parameters, you see that the convergence is less accurate. Okay, and in practice, I cannot do that. I cannot know that because in practice, I do not know the answer. I do not know the dashed line. Okay, so how can I know that the solution is worse? Okay, here the algorithm gives you an indication showing you that the variance here is larger, and therefore it tells you, okay, I'm less confident in these results than in this one. Okay. So that's a partial answer to the question. So we also applied this to real data. And then, as Philippe said this morning, we have many other difficulties to fix. And the first difficulty is quite interesting, is that we do not have to forget that in real life, we are under pressure. Our arteries are under pressure. Okay, so when you take an image on a patient, what you see is not a stress-free state. So from the mechanical point of view, that's very important. Okay, and it's funny to see that in the literature, you can see many works dealing with complex biomechanical constitutive law for the arteries, nonlinear constitutive law. But if you forget what I've just said, you can have a very sophisticated nonlinear law. Okay, if you take it at the wrong place, it's completely false. Okay, if you do not take into account that your solid is pre-stress, your nonlinear law is completely out. It's better to have a linear law around the correct state than a nonlinear law around a state that is wrong. Okay, so the first issue is to be able to recover this state, having as an assumption that you cannot kill your patient to have a stress-free state. Okay, so you have to solve a first inverse problem to go back to a reference configuration. Second difficulty was presented by Philippe this morning in the case of the myocardium displacement, is that in general, you do not have the displacement, really. You could have the displacement, for example, with these tagged MRI techniques for the myocardium, but as Philippe said, this is not routine today. And for the artery, to my knowledge, it is not used. So we do not have the displacement. You do not know the displacement of the material point. What you know is the normal displacement of the point, not the tangential displacement. Okay, and so this really make questionable what is called in the literature image-driven FSI, because many groups decide that FSI is too complicated to solve, and they say, okay, I have the images that give me the movement of the artery, so I do not have to worry about FSI, I just enforce the observation I have on the displacement of the artery. But these observations do not carry the displacement. It only carries the normal displacement. So you miss the tangential part, and you miss what makes your fluid. Imagine I just turn this bottle around its axis. Okay, if I take an image of that, there will be no movement. Okay, but this movement makes the water move inside. So if I miss the tangential displacement, I miss basically everything here in that case. Okay, so that's really something that has to be deal with. And so in that case, we use, as Philippe explained, the distance between the surfaces. And the third difficulty will allow me to answer to a question I had yesterday about the fact that the arteries are not isolated. And so I give you my favorite example in this data assimilation problem. These data are taken from an abdominal aorta. Okay, and you can see, so the vector represents the displacement. So you cut the aorta that way, okay, and you look at the section. And you can see that the displacement are not the same depending on the region you consider in the circumference here. There is a strong dissymmetry. Okay. Assume that you want to solve a data assimilation problem where your question is, what is the stiffness of the artery? And you want to match these measurements. The answer of the data assimilation is clear. The stiffness of the artery will be larger in that region than in this one, which explains why you have a lower movement here than here. Okay, that makes sense. The problem is, it's not the physical reason of this difference. Okay, the physical reason of this difference is that this region lies on the backbones. Okay, you have the bones here, which explain why you have a different displacement here compared than here. Okay, so you can do data assimilation on the wrong model, and you can get a perfect matching with your data. Okay, so I just emphasize this example because we do not have to be misled by data assimilation. It's not because you match your data that your model is validated. Okay, and so in that case, you can match perfectly the data with the wrong model. This means nothing about the model, of course. The artery is not stiffer here than here. It's just that the external tissue are not the same. Okay, and so we have to take this into account. Of course, we cannot model everything in the body, so we will take it into account in a very simple way. So instead of taking a constant pressure, we will take these boundary conditions, which are some sort of a Robin boundary condition that will model distributed spring and dashpots outside the artery. And so this will give the answer to the question, to the problem I had yesterday. You remember the strange movement of the carotid artery that was due to the fact that I used a constant pressure outside. Now with this very simple external tissue model, you recover something that looks more realistic. And something that can be estimated, again, with the data assimilation procedure. Okay, so this is the example we run with this external tissue support model. And these are some comparison between the image and the displacement. Again, I do not claim that this is a validation of the model. Okay, I just claim that the algorithm was able to converge to something that first give us some almost constant coefficient. So it's a good indication on the fact that your model is reasonable. When your coefficient do not have to oscillate to match the measurements. Okay, so we converge to something. And the discrepancy between the data and the model are reduced. So in that case, it's not a validation, but we were able to validate it in some experimental, with an experimental device. Here, this is a silicon tube with different stiffness on the boundary. In that case, we know the solution, we applied the same methodology, and we were able to recover the different stiffness on the tube. And finally, we tested it now on real data coming from MRI. And again, here we cannot validate it in the sense that we do not have a ground truth that allows us to compare the measurement, the solution of the model everywhere, okay? But here we made an estimation on these 5 different regions, and you see that the coefficient first moves a lot, and then they converge to some value, which is, again, not a validation, but a good indication that the model is able at least to reproduce what is observed. Okay, and I will finish now with something that I consider as a validation, and this is a work that we did in particular with Benoît Fabrège, who is here. This is a validation in the sense that the model was really used to make a prediction. This is why we use model. It's to make prediction. Okay, we use model based on physics to have some capacity to make prediction. If you are just able to recover what you have measured, this is not useful. Okay, so this was proposed in a challenge organized in the framework of a conference where some data were released. The data typically here are the inflow, the flow rate at the inlet, the flow rate at the outlet, the flow rate here in the mean flow rate on the 3 top arteries, and the pressure measured at the inlet. And the challenge was to measure the pressure drop, because this is a pathological case. There is a coarctation, and this is the occasion for me to close the loop with what the first example I gave you yesterday. So this is the problem of coarctation. As I told you, the difficulty is to understand if the coarctation really induce a problem to the patient or not, at stress, at exercise, or at rest. Okay? And so the question is, what is the pressure drop? This was the challenge. Of course, the pressure at the outlet was not given. This has to be predicted by the model. So here, we did not run a full field structure iteration because it was considered as too complicated, and probably there would have been only a few groups would have participated to the challenge. So it was only fluid simulation, but we took into account fluid structure by introducing a sort of capacitance to mimic FSI. And so we used the 0D abstraction of the model, and we estimated 14 parameters. Okay, so it's a lot. Just by the way, an interesting aspect of experimental data. As I told you, there were measures of pressure and flow rate, and the people who took the pressure did not align in time the measurements, in the sense that the pressure was measured independently of the flow rate, and they didn't make the alignment of the time. Okay, so that's a problem when you try to do data assimilation. If the different quantity you measure are not aligned in time, you have trouble. And so here the solution we took was to introduce a time shift as a new parameter of the model. Okay, as an unknown of the problem. Okay, and here is the result we get. So we can, as I told you, there is a solution at rest and a stress solution at exercise. So let's focus on the solution at exercise, since it's easier to comment. So the black lines are the measurements. So here, the continuous black line is the pressure at the inlet, and the dashed black line is the pressure at the outlet, which was not given. Okay, it was given only after the challenge. So the red curve here is the pressure at the inlet. So we try to set the parameters in order to have a pressure at the inlet which matches the pressure measured. Okay, And then we observed the pressure. I mean, we get as a solution of the simulation the blue curve, which is the pressure at the outlet. And this was the one that we were looking for. So the agreement between the two curves is not extraordinary, but you have to take in mind that the clinical interesting quantity is the difference. It's a pressure drop, okay? So you can see that the pressure drop between the two black curves is not too far from the pressure drop between the red and the blue black curve, and the blue curve, okay? So in that case, we can say, okay, the model is validated in the sense that, not in the sense that every single vortex in the fluid has been validated compared to a complex measurement or whatever. No, it's validated in the sense that the model is able to predict something that wasn't known at first and that could be compared to something that were measured, okay? And the prediction was, sufficiently correct to be used for a clinical decision, for example. So with that, I will finish. So just to summarize, data assimilation allows us to reduce uncertainties and to enrich the data with physical-based model. Keep in mind the divergence-free property of the velocity, for example. Two families of methods, variational, sequential. Here I have presented the sequential methods. The benefit of sequential algorithm is simplicity of implementation. Do not have to implement complex adjoint problem to compute tangent or whatever. But difficult or intractable for large systems. So this mixing with Leuenberger observer, which by the way is called the nudging in some communities, and a nonlinear Kalman filter. And among the numerous research topics, I will just mention two. First, we will have to adapt these assimilation algorithms to new kind of medical data. And there are many medical data that we are not yet able to assimilate in our models, in particular those coming from ultrasound, Doppler, okay, ecography, would be very useful to do data assimilation in the fluid. And also a very important question that we did for another problem in cardiac electrophysiology with Philippe too, is to leverage the information of multi-physics system. Because when you do multi-physics, you work more to solve the direct problem, but for the inverse problem, you have access to more measurements. Okay, and so that's a very interesting aspect. Work more to have a more complex problem, but then use more measurements to do your data assimilation. So being able to take advantage of this is a very interesting question for many problems. And with that, I thank you for your attention.